Ooh, a hushed silence. Well, welcome everybody. We're packed to the gunnels. There's one more space, two more spaces at the front here if anybody's looking for a chair. Right. Well, welcome to the Geological Society of London and to this, the 10th Shell London lecture for 2012, entitled Incoming, Learning to Love the Meteorite. My name is David Shilston. I'm president of the Society, and it's my pleasure to thank Shell UK for making this series of public lectures possible. Meteorites have been the stuff of legend throughout human history, and since 1980, the ideas that dinosaurs were wiped out by a meteorite strike at the end of the Cretaceous period has become one of the most widely known scientific ideas of all. However, the causes of that mass extinction were complex, and major meteorite strikes are always bad news for Earth, as a hypothesis is being challenged with fresh discoveries. New research suggests that 470 million years ago, a stupendous collision in the Asteroid Belt bombarded the Earth with meteorites of all sizes. A revolutionary idea is emerging that the resulting ecological disturbance may have been responsible for the single greatest increase in biological diversity since the origin of complex life. This is the hitherto unexplained Great Ordovician Biodiversity Event. Dr Ted Nield, today's speaker, has written a book about this subject. Ted studied geology at Swansea and Cardiff and then worked briefly in the oil industry before becoming a science journalist, writing for New Scientist and most of the UK Broad Street newspapers. Ted published 2 textbooks on paleontology for Pergamon Press in the 1980s, and his 1997 comic novel, Dead Clever, was serialised in the Times Higher Education Supplement. He is now editor of our magazine, of the Society's magazine, Geoscientist. Ted's book, Supercontinent, 10 Billion Years in the Life of Our Planet, was published by Granta in 2007 and has since come out in the USA and been translated into 5 languages. Now, Incoming, or Why We Should Stop Worrying and Learn to Love the Meteorite, appeared in the UK and America in 2011. Ted was chair of the Association of British Science Writers for a couple of years and of the United Nations International Year of Planet Earth, the outreach program 2001 to 2008. And in 2007, he joined Whoopi Goldberg, I have to read this, Whoopi Goldberg, Bing Crosby, Muhammad Ali, Pope John II, and of course, Colonel Sanders, in being created a colonel of the Commonwealth of Kentucky. Ladies and gentlemen, please welcome Colonel Ted Nield.
Thank you, David, and evening all. It may come as a surprise to you to learn, I mean, it did to me, that, we're familiar with the phenomenon of getting a bit fatter as we get older. But the Earth is getting fatter as she gets older, but at the rate of about 30 to 40,000 tons every day. That's the meteorite flux. The Earth is getting heavier, but of course it's actually negligible because if you can imagine the impossible situation of weighing the Earth in its own gravity, the Earth weighs 6,000 billion tons, so it's negligible. Most of the stuff that comes in to make that 30 to 40,000 tons every day is mere dust, and it's too small even to make shooting stars. It just drifts into the atmosphere. But some, of course, can be rather larger. Which is forward and which is back. Oh, there we go. There's a friendly. That's just to make sure it works. Some are big enough to create fireballs in the atmosphere and make it through that protective shield to the Earth. Now, this is the largest known iron mass on the face of the Earth. It's the Hoba meteorite, with my mother-in-law for scale, in Namibia. Now, some are very few, fortunately, because as usual, the bigger the fewer, Some are so large that the atmosphere doesn't slow them up very much as they cross it. And so they reach the ground with most of their cosmic velocity still intact. Now, I want to have a word about cosmic velocity with you because apart from being one of the great unused titles for a rock group, cosmic velocity is really quite something stupendous. And we're talking here about 40 kilometers per second. And very often the combined impact speeds are higher even than that. So a very large asteroid will not be slowed up very much by the atmosphere. And you can imagine that if something 10 kilometers across is coming in at that sort of speed, there is a split second, about a quarter of a second, when the front end of the meteorite is touching the ground while its back end is still in space. Everything moves very, very fast in space, in other words, so I just want to sort of get that established. Of course, it moves very fast because there's nothing to stop it. But of course, space is huge, so it really has to move very fast, because if it didn't, it would never get anywhere. Now, when something 10 kilometers across hits the ground, with all that kinetic energy embodied within it, then, of course, the first thing that happens is that it immediately flashes to heat, and all that heat ends up in the atmosphere. But the point I want to establish here is that the environment that we live in is actually quite close to space. Space is not very far away. We think it's far away because of all the fuss that we have to go through to overcome gravity. But actually, if Vauxhall Cavaliers could do up as well as they can do across, you could actually be in space in about 40 minutes without breaking the speed limit. So it's really rather close, and it's all part of our environment. It's not something very remote from us. So imagine all that kinetic energy flashing to heat. It creates a fireball, an explosion, which is bigger than all the nuclear arsenals of the world being set off at once. And it has a pretty devastating effect when that happens. Now, in my book, and I suppose it's a good idea to get the commercial over with first, the book is called Incoming, I examine two things in parallel. Oh, and I should also mention, because it might be significant later, it's also called The Falling Sky. That's the American edition, which is slightly superior to the British edition in that it has one fewer embarrassing errors in it. But in this book, I examine two themes in parallel. One is the effect of meteorites on the history of life. We all know that that an impact had a lot to do with the disappearance of dinosaurs 65 million years ago, but I also describe some very exciting new research which has revealed that 450 or so million years ago, the Earth was bombarded by meteorites at such a rate that we can actually find them fossilized in rocks. And yet then there was no mass extinction. Quite the reverse, in fact. It was one of those times when life underwent one of its major radiations. So how can these two things, both be true? The second theme of the book is the history of ideas about meteorites, from the earliest times right up to the present. Rather like shooting stars, ideas flash across the human the firmament of the human mind all the time, 40,000 tons a day. But only at certain times in human history do those ideas really sort of amount to something. There's a timeliness, in other words, about ideas, just as there appears to be in the arrival of meteorites and the effects that they have. So, meteorites. Well, nearly all meteorite material comes from one place. It comes from the Asteroid Belt. And this is a débris field that lies between the orbits of Mars, the outermost rocky planet, and Jupiter, the biggest of the gas giants. But there are many different types of meteorites. I don't propose to go into them here. That would be a lecture all into itself. But the thing to know about them is that they are all very, very old. They are, in fact, the oldest things that it is possible to hold in your hand. Oh, and I shall do that now. Here is a meteorite. These are great things to take through airport security. I've been traveling. I should write a book called Travels with My Meteorite. Excuse me, sir, you appear to have something extremely dense in your luggage. Yes, I know. Could you explain it to us, please? Yes, it's a meteorite. Oh, is it? Yes, it's an oriented nickel-iron meteorite. Weighs about 0.5 kilogram. It's got a clear nose cone, So you can see how it came powering down through the atmosphere like that, and it's got beautiful radial regmaglypts, as they're known, thumb-shaped depressions, which are due to the ablation of the surface by the atmosphere as it comes through. And they say, oh, very nice. And do you know that that's the oldest thing that you can possibly hold in your hand? It's the oldest thing that there is. At this point, the gentleman dropped it, and said, oh, I'm terribly sorry. I was, well, considering where it comes from, you really don't have to worry. I'll put it back on here. Feel free to come up and stroke it later. Meteorites are stray fragments of asteroids or complete asteroids. They're the leftover stuff out of which the planets accreted from that swirling disk of dust and gas that was the protoplanetary nebula surrounding the early sun, and which coalesced into bigger and bigger orbiting bodies, creating our solar system. And when did this happen? Well, I mean, if you perform a radiometric dating exercise on a meteorite like that, you come out with the oldest known date, the date taken as the origin of the planets, and therefore the maximum age of the Earth, which is easy to remember. At least it was until some fool went along and did some more accurate research and made it unmemorable, but never mind, they only changed it by a bit, and it's 4,567 million years, or 4.5 billion. So, to begin, I would like to take you back in time, you won't be surprised to hear, to an era completely different from our own, when almost nothing that we now know and take for granted existed, and which now seems unimaginably alien and weird. I mean, of course, the 1970s. Now, this was a very different world from the world that we now inhabit. At that time in Britain, it was not normal for students, or indeed anyone else, at least in the provinces, to shower more than once a week. And those who did caused comment, which is why I remember it. Nor had anybody, unless they'd actually visited the United States, ever seen a McDonald's, the very first one, there it is, on Power Street in Woolwich, opened for burgers and fries in 1974. For the first time, the great British public saw a really clean restaurant, and they mistook it for glamour. Can you believe it? Well, anyway, it's surely no more remarkable that at that time, paleontologists were reluctant to talk about mass extinctions. Today, by contrast, it can be hard to get them to talk about anything else. Following Charles Lyell, paleontologists had grown used to rationalizing sudden events like mass extinctions out of existence. Perhaps they only appeared sudden because of slower deposition. So everything goes on at the normal rate, but suddenly sedimentation seems to cease or become very slow, and then it suddenly carries on, and so it appears that you have a sudden jump. Maybe they were just brief quickenings of standard processes, or maybe they were artificial. There is a certain amount of truth in this. Paleontologists are very territorial people. They tend to work on rocks of a certain age, and they don't tend to stray into other areas, at least not then. So perhaps extinctions were self-imposed disciplinary boundaries. And the way that my old professor, Derek Ager, sorry, that's Charles Lyell. Charles Lyell, you notice, came very gradually. Derek Ager is going to come with a bit more of a rush. At least he will when this works. Come on, Derek. I'm pressing the right button. Oh, there we go. There he is. Right, Derek Ager. So, the way he wrote about mass extinctions, he wrote, "There is no point in denying them," shows that at that time that's what paleontologists mostly did. I was lucky in my teacher because Derek was the geologist who perhaps did most to rehabilitate the rare event in geological history into uniformitarianism. That was his main and lasting contribution to the way we all think about Earth history today. But even so, he hardly ever mentioned meteorites. Such ideas back in the 1970s took a scientist very close to the edge. Comets, meteorites, supernovae, spiral arms of the galaxy, clouds of cosmic dust, all that sort of thing, were highly distasteful as geological agents in those days. People thought of space as being not part of our environment. It was somewhere else. By contrast, they were the mainstay of the lunatic pseudo-scientific fringe of the time, with whose outpourings bookshelves of the 1970s were groaning as were the geologists who read them occasionally. Now, Eric von Daniken, for example, you may remember him, explained history by invoking aliens in Chariots of the God in 1968, and of course not to mention Immanuel Velikovsky, whose books were written in the 1950s, but they took on a new lease of life in the 1970s in the alternative culture. And if the risk of being compared in any sort of way to these lunatics was not enough to discourage a legitimate scientist from considering cosmic influences, there was yet another factor, and that was the parsimonious instinct of the true scientist. Now, you'll know, I'm sure, that one of science's central assumptions, which rarely leads physicists astray when they deal with their subject, is Occam's razor. The simplest explanation for anything is probably right. The classic example being the Ptolemaic versus the Copernican system of the explanation of the retrograde motion of planets, for example. If you assume that the sun is at the center, everything can be perfectly explained very simply, but if you assume that the Earth is at the center, in order to explain the retrograde motion of planets, you have to put epicycles in, and it all gets terribly complicated. And that's the classic example of Occam's razor. It rarely leads a physicist astray. At that time, though, Occam's razor was taken by geologists to mean that looking outside the Earth for any explanation of what happened upon it wasn't proper. It was somehow a kind of deus ex machina. Even worse than that, perhaps possibly, it was straying into somebody else's discipline. Now, in those days, disciplinary boundaries, which now happily seem what they are, which is completely arbitrary, they felt like iron curtains ordained by God, or somebody at least. But although Derek remained chary of meteorites, there were others who were younger and had far less credibility at stake were not. And Ager had this habit of drawing towards him students who were eager to work in the new field of NeoCatastrophism. And I can well remember the sort of frisson of forbidden delight that passed through a lecture theatre in Swansea one evening when one of these students, the late Richard Hodgkinson, who came to us sprinkled already with the stardust of having worked at NASA, delivered a seminar about his hunt for overlooked impact craters on the face of the Earth. Even admitting their existence in any number in those days was really a complete heresy. Yet, only 5 years later, by which time I was a research student, I found myself listening to much wilder ideas without turning a hair, including one that suggested that extinctions happened every 26 million years, for example, when cometary objects were catapulted out of their peaceful existence outside the solar system by a mysterious companion star to the sun, which had been evocatively dubbed Nemesis. There's a whole book about that. Never came to anything, of course. Derek Ager's neocatastrophist revolution really did triumph quite quickly eventually, but this is the way that science works. The context suddenly changed, science was ready, and in 1980 catastrophism really came home to roost with a vengeance, because not very far from Siena, the Tuscan city, by coincidence, where for the first time in history in 1794, meteorites rained out on professors' heads instead of the heads of peasants, and forced them to take them seriously for the first time. Just outside that town is the Battacioni Gorge, where rocks that span the end of the Cretaceous period and the early Paleocene are exposed. Now, at 347.6 meters in the measured section lay what we all now know as the KT boundary, a band of clay, only about 2 centimeters thick. Geologists Walter Alvarez and Terry Engelder took the crucial sample of this in 1977. Now, as you can see from that photograph, clay partings between the limestones are quite common, but this one was thicker than all the others, and it wasn't just any old clay parting. It marked the boundary not only between two geological periods, remember, but between the Mesozoic and the Cenozoic eras, when fossils of middle life gave way to those of recent life, including hippopotamuses, aardvarks, and us. So the question that Walter Alvarez wanted to sort out was, how long did that clay take to be laid down? Because this was a crucial question, because slow deposition would have meant a slow mass extinction, and the suddenness, therefore, only apparent. Lyell would have approved of that. But if the reverse were true, then the extinction would have been genuinely fast. And so he wanted to tie down exactly how fast that parting took to be laid down, what time, sort of time interval. But then there's fast and fast, of course. Was it perhaps geologically fast, which means less than 1 million years? Or was it archaeologically fast, which would be less than 1,000 years? Or was it human life fast, last Tuesday afternoon? Now, in order to find out what Walter needed was an accurate measure of depositional rate. And that brought him back into contact with his illustrious father, on the left in the picture, the Nobel Prize-winning nuclear physicist, Luis Alvarez. Now, Luis knew that in order to sort this question out, what he needed was something that accumulated always and everywhere on Earth at the same rate all the time. And the element iridium he hit upon because it was rare on Earth but abundant in space. And it rains down on us all the time at a pretty constant rate, 30 to 40,000 tons a day. So if you measured the amount of iridium in the clay, if the clay was recording a slowdown in deposition, then you would show elevated amounts of iridium. Whereas if the normal sedimentation rate applied, then you'd have normal concentrations of iridium. So what a guy called Frank Asaro found when he actually did the geochemical analysis on this absolutely astonished him. He initially reported 3 parts of iridium per billion. Now that doesn't sound like very much, but that was not just high, it was enormous. So, doubting his results like a good scientist, he redid the experiments. And sure enough, he'd made a mistake. It should actually have been 9 parts per billion. In other words, 90 times higher than the highest expectation that had been given to him by Luis. And what he discovered, of course, was the iridium anomaly and the answer to a question that nobody until then had been asking. Now, over the summer of 1979, Luis Alvarez, who worked on the atom bomb with Robert Oppenheimer and Edward Teller on the Manhattan Project, and he'd actually flown on the mission that dropped Little Boy, the uranium weapon that devastated Hiroshima. Now he wasn't on the Enola Gay. He was on the plane that followed. He designed actually some of the testing equipment that they dropped to measure the yield and so on. He began to develop ideas over 1979 summer about how a truly gigantic extraterrestrial impact might have created a worldwide iridium anomaly, killing the ammonites in the oceans and the dinosaurs on the floodplain and all the other things that also perished at the end of the Cretaceous. And what we may refer to as the full Alvarez theory would hold that this one impact was enough to do everything, unaided. And then, of course, being a physicist, he wasn't interested in just telling a story about something that happened once. Being a physicist, he wanted to have an overarching theory which explained lots of things. And so the next question is, well, maybe impacts also caused other extinctions. Maybe they caused all mass extinctions. Well, of course, Steve Gould told us that nearly all hot ideas turn out to be wrong, or at least partly wrong. And since 1980 and 3 decades of intensive research, we can now confidently say that no other mass extinction in history has any extraterrestrial connection at all. We do know, though, that all of them coincided with the eruption of large igneous provinces, which is a fact that's been mostly revealed by the guy there with the mischievous look, Vincent Courtillot of the Institut de Physique du Globe in Paris. And he, with another geologist called Goethe Keller, who has always had trouble with the full Alvarez theory, they are currently working on dating the Deccan traps in India with what they hope will be unprecedented accuracy. Their work is not yet fully published, but it is suggesting that the main phase of eruption, of that stupendous eruption, took place in possibly as little as 10 to 30,000 years, and right at the end of the Cretaceous too. Which brings me back to Derek Hager. Now, long before the Alvarez theory broke, Derek wrote that all mass extinctions were likely to have been due to a combination of factors. He thought, well, the world is full of cyclicities. Everything works on a cycle, and most of them, nearly all the time, are out of phase. But now and then, they coincide. They're bound to. just by the laws of statistics. And that is when you get a mass extinction. At the end of the Cretaceous, one of those causes, according to this explanation, coming on top of massive volcanism with all its toxic gas and acid rain, and a variety of minor causes like the fact that there was a short coastline. This means a lot to shallow marine mammals and shallow marine animals rather. Short coastlines. We had a supercontinent at the time, Pangaea, ocean anoxia, which was widespread. On top of that, there was also a meteorite impact. Life had been, in other words, on its knees already, and the impact merely put the seal on the inevitable fate of the dinosaurs and everything else. Now, so let's leave that for a time being and think about the Ordovician. To tell the story of how the meteorites of the 470 million years ago were discovered, we have to travel back even further in time. Not to the Ordovician, though, but to the 1950s. In 1952, a Swedish geologist called Per Torslund at the University of Uppsala received a polished slab of limestone. There it is. It's about 65 centimeters square, and it comes from a place called Brunflo in central Sweden. And this particular slab was unusual because, as well as all the usual fossils, the brownish red rock, it's a limestone, but it's high in iron content, it's a condensed deposit, contained a large black mass about 10 centimeters across. Now, the limestone had formed in a shallow sea, which had then covered the area, under waters a few hundred meters deep. The water had been clear, free from any terrigenous sediment input, apart from wind-blown dust. The limestones accumulated, therefore, very slowly, incredibly slowly, as shelly organisms died and settled out and mixed with the red dust. So finding a 10-centimeter diameter boulder, no matter what its composition, in that sort of sedimentary environment, many kilometers from any ancient shoreline, was unexpected, to say the least. Well, no one could explain it. And so, as usually happens with these things, it was hidden away in the basement, where it wouldn't embarrass anybody. And it stayed there for 25 years. Now, often what's needed when there is an impasse like this in science is a conceptual leap. And this came in the 1970s, as more and more geologists, many of them Derek Eger's students, were successfully tracking down and identifying Earth's previously unrecognized impact craters. And 200 kilometers south of Brunflo, there's a circular geological structure called the Siljan Ring, which was only just then being recognized for what it was, as an ancient, massive impact crater. Now, this reached the news, and it streaked through Per Torslund's mind just as he was rearranging his working collection in December 1979. And Torslund re-examined the object, as he wrote later, with the idea in mind that it might be a meteorite. Sure enough, believing something to be possible renders things visible, and the mysterious black boulder did turn out indeed to be a fossilized meteorite. Now, Brunflo might have remained an isolated curiosity, but in 1988, in slightly older limestones, another one turned up. But that's getting a bit ahead of the story. Back in the 1970s, between 1970 and 1979, at about the time that Torslund was re-evaluating his mysterious slab, I was beginning my doctoral research in Sweden. And in fact, I briefly met Per Torslund on a tour that I made of Stockholm and Uppsala, just to sort of get to know people. And in the year that I was coming to finish my PhD, a Swedish student called Birger Schmitz embarked on his own PhD study at Lund University, where he is now professor. Now, Schmitz had read the then newly published paper by the Alvarezes, Helen Michael and Frank Azzaro, on the KT impact hypothesis, and immediately realizing that this, like again, any good scientist, realizing this is the biggest story in town, he changed his whole research topic. His supervisor did not like it, but, well, what can you do? Eventually, the two met. He'd published a few papers by this time, Schmitz that is, and Luis happened to be in Stockholm as a Nobel Prize winner. You know, you turn up in Stockholm and the Academy gives you a dinner. So he was turning up, showing his latest girlfriend around actually, and he had a dinner. And the only person he wanted to see at this dinner was Birger Schmidt's. And the upshot of all this was that Luis invited Birger Schmidt's to Berkeley to do his postdoc there. And at the end of that period, Schmidt's returned to Sweden, mentally prepared, you might think, for what was about to emerge thick and fast, as it turned out, from the Ordovician limestones of Sweden. Schmidt soon heard about the second fossil meteorite, and before long he had begun a systematic sampling campaign, which since 1993, now I'm talking, I wrote this in 2007, they're finding more every year, but by 2007, no, 2009, I beg your pardon, they had found no less than 90 fossilized meteorites. They're all the same type of meteorite. They're known as the L-chondrites, which is one of the most common species of meteorite that falls even today. Now, 90 sounds like a lot of fossil meteorites. It doesn't, what can possibly be rarer than a fossil meteorite? But there are 90 of them. It sounds like a lot, but what is a lot? What is a lot of meteorites? We know what the Earth's meteorite flux is, 30 to 40,000 tons a day, the sort of normal background rate at which things arrive from space. Taking that as a starting point, Schmitz did some calculations, and he compared areas, sedimentation rates, numbers of meteorite finds in so much thickness of rock, known to have taken so long to deposit, and so on. And he calculated that in the 3 million years after the bombardment began, it actually began 480 million years ago, the meteorite flux of the Earth rose several hundred times and remained 10 times greater than it is today for 10 million years. At its peak, the meteorite flux reached at least 100 to 150 times present values. So the Earth was being bombarded for several millions of years by meteorites ranging in size from the very minute to perhaps the sort of Chicxulub enormous. That 10 million year period covers the estimated ages of no less than 4 major impact craters in Scandinavia alone, Lochner, Kerdia, Tveran and Granby. Now, working backwards from the meteorite abundances, Schmitz estimated the size of the original parent body of this meteorite storm at least 100 to 150 kilometers. So an asteroid 100 to 150 kilometers in diameter. It must have been one body because all the meteorites are of the same composition. After the collision, the exploded fragments would then have given rise to an asteroid family, which orbits together. This is what happens when two asteroids collide. The fragments fly apart. Gravitational forces tend to hold them in a kind of a cloud. They then orbit in like a flock of geese together. They form an asteroid family. There are many of these families, but in 2009 we even managed to find out which one was the parent asteroid family of all this material that is still landing on Earth even to this day, and it's the Gefion family. And we know this is rather neat, because the light that reflects off those asteroid bodies matches the reflectance spectrum of the L-chondrite meteorite. So if you take an L-chondrite meteorite and you bounce light off it and you analyze the spectrum, you get exactly the same curve that you would do if you measure the spectrum of the reflected light from the Gefion family asteroids. They match each other really quite well. Now, the Gefion family's age, because the Gefion family had been known for some time, and astronomers had already estimated the age of the Gefion family from other evidence at 485 million years. And the diameter of the parent body, which they had estimated by broadly putting back all the bits back together and to see how much they had already estimated that the original body would have been 100 to 150 kilometers across. So all this seemed to fit. Okay, so much for the astronomical side. So what effect did this huge and prolonged bombardment have upon life on Earth? Well, surprisingly perhaps, the bombardment coincides precisely with the greatest burst in biodiversity in the entire geological record, which is the Great Ordovician Biodiversity Event. Now, this event had been uncovered by the late Jack Sapkowski. He's the guy with the glasses. who was the first guy to enter time range data for fossil species into a computer database, starting in the 1980s. And he used this to draw graphs of how global biodiversity went up and down through time. And that's what you see there. Now, as expected, this graph picks up the 5 big extinctions. You can see them quite clearly. But it also revealed for the first time a completely unexplained and unexpected rise in biodiversity just there during the mid-Ordovician. Now, all the other great increases in biodiversity happen after a mass extinction. It's a rebound effect, but not this one. This one just seems to take off just for its own, just for the fun of it. So if you close in for more detail, this is what it looks like, translated to the timescale of the Middle Ordovician, where we can see, this is Berger-Schmitz's own diagram, the precise correlation between the arrival of the first meteorites, which is just there, and the jump in speciation, and also a rise in extinction rates amongst all taxa. So the red spike is showing you extinction rates, and the biodiversity, the speciation rate is shown by the top black line. So the two things go together. You have a peak in speciation and also a peak in extinction. So, why did this bombardment give rise to increasing biodiversity while the end Cretaceous impact or impacts helped to make an extinction? So it's now time to meet somebody else, an Estonian astronomer and astrophysicist called Erenjulius Epic. Now you'll all probably know his grandson, Lembit, who was until fairly recently the Liberal Democrat MP from Montgomeryshire, probably will be again one day, although I'm not so sure now, who played a major part in establishing the UK arm of the International Project Space Guard. People thought at the time, why is one of our MPs so worried about asteroids? But of course the reason is it's in the family. And Project Space Guard is there to search for asteroids that might hit us. Now, Ernst Epic's speciality were asteroids and comets. As long ago as the 1950s, he saw that impacts might have affected life in the past. Though he was concerned less with sort of global carnage, total devastation and mass extinction, than with localized, you might call extending the nuclear warhead analogy, limited theatre impacts. If an impact devastates a smallish area, it could, for example, kill off an entire species endemic to that area. So, Big Bang in Australia kills off all the kangaroos. So if the object, much of animal and plant distribution on Earth is provincial in that way. Distribution is not universal for most species. And for those organisms, extinction by impact need not necessarily mean that there had been a global catastrophe. Epic's limited theatre impacts did not cause mass extinctions, but in his idea that they would sterilize large areas of the planet and leave them open to fresh colonization, they would loosen or even perhaps release the stranglehold that endemic species would have had and allow opportunistic new species to come in, species that had hitherto been denied a foothold, to enter this area and to thrive, thereby increasing global biodiversity and translating through time into evolutionary diversification. Now, this is actually a phenomenon well known to ecologists. It's called intermediate disturbance theory, and it's a phenomenon that I saw operating in my PhD research on the biodiversity increase seen in Silurian reefs on the Swedish island of Gotland. To bring a sort of down-to-earth example, you see it when quarrying creates a cliff or a wetland habitat that previously didn't exist in an area. It attracts in species that were not previously seen there. Butterfly species are more common in coppiced woodland than they are in uncoppiced woodland. Physical disturbance of the environment, as long as it isn't too severe, stimulates biodiversity by increasing diversity of habitat. So, although statistically at least one of the many impacts during those 10 million years of the mid-Ordovician could have been Chicxulub-sized, the effect that it would have had on the thriving ecosystem of the balmy mid-Ordovician was quite different from the effect that a big impact would have at the end of the Cretaceous. the mid-Ordovician was a very different world. There was no large igneous province being erupted. It was not a poisoned, anoxic, choking, acid rain spattered hothouse world like the late Cretaceous. The same agency, but in a different context, produces a different result. I began to think about this talk on, by coincidence, on November the 11th, Armistice Day. And I thought about Gavrilo Princip squeezing the trigger on the 28th of June 1914 and sparking the Great War. If you think about that system, the system starts with the gun. The bullets emerge from the muzzle of the gun with a very high level of mathematical certainty. You pull the trigger, bullet comes out, you know how fast it's going. It's a simple system, trigger, cap, explosion. It's cause and effect. It's pure and simple. It's physics. The effect that those bullets had on the bodies of the Archduke Franz Ferdinand and his wife Sophie on that summer day, you know, they were fairly predictable, but not so certain. People do survive gunshot wounds, so you might have missed. Maybe the chauffeur got in the way, or who knows, slightly more uncertain. But the tertiary effects, that the death of these two people should drag the world into a great war and see 20 million people dead and bring extinction to the old historic order of Europe, that would have been even more, that's even more uncertain, because now we're talking about the effects of a single event on a very complex system, human society. And in that situation, the outcome of any particular act depends not so much upon the act itself as upon the context in which it happens. Geologists may be writing the story of the Earth, but their science remains basically history, a tale of how a complex system, the Earth and life upon it, unfolded through time, steered by chance events that were themselves not inevitable, just because they turned out subsequently to have been significant. Working out cause and effect in geological history is very hard to do. The further back we go, the less comparable the modern Earth is with the Earth that we're looking at. Life today is not as it was 50 million years ago, let alone 300 or 400 or 500 million years ago. A meteorite impact today need not, therefore, produce the same effect on our changed planet with its changed biosphere. So, I say again, while in physics, the simpler an explanation is, the more likely it is to be correct, in history, the simpler an explanation is, the more likely it is to be incorrect. History is allowed to be complicated. The historian H.A.L. Fisher wrote in his History of Europe, men wiser than I have discerned in history a plot, a rhythm, a predetermined pattern. Those harmonies are concealed from me. I can see only emergency following upon another, as wave follows upon wave. In other words, the only basic law in history is shit happens. The consequences of meteorite falls and of ideas about them, just like the consequences of the shooting in Sarajevo, are created largely, or possibly entirely, by the context in which those events or those ideas occur. And that applies to the Earth as well as to human society, because both of them are complex, evolving systems. Shakespeare wrote in Cymbeline, "Fear no more the lightning flash, nor the dreaded thunderstone." And that is the message I would like to leave you with. Meteorites are a force of nature. In themselves, they're neither good nor evil. They may have helped to bring life to our planet in the first place. They helped put the dinosaurs out of the way, which was bad news for them, but it's okay for us. Dinosaurs would probably have had their day anyway, in my view. Meteorites may even have given a kick in the genes when life most needed it, and helped to fill the world with more complex life in the mid-Ordovician. So our wise attempts since 1980 to map near-Earth objects in Project SpaceGuard has done us the great service of reducing the estimated risk of death by meteorite to something on the same level as death by firework. So it now stands at, this is a global risk, mind, of 1 in 720,000. Something we're all happy to live with. And don't forget, in all of reliably recorded history, nobody absolutely nobody has ever been killed by a meteorite. So I wouldn't advocate that we stop watching the skies, but if we do one day see one coming, there are at least plausible science fiction scenarios that could enable us to deflect them in time. But if we wish to worry fruitfully about things, other than things like the Mayan calendar, and being a practical sort of chap, I think if we are going to waste our time worrying about things, we ought to worry about things that we can actually do something about. And if we wanted to worry about the main thing that threatens our existence on this planet, we needn't search for it in outer space. It's actually sitting next to you because it's us. Thank you. But there is more about all this. If you're really fascinated by this subject, there is a major international conference taking place at the Natural History Museum next year, and it's got a lovely, easy to remember URL where you can go and express your interest in attending. It's called massextinction.princeton.edu. So there you are. Gerta Keller herself will be appearing. So. Thank you very much.
Well, it's safe to remain in here a little bit longer, I think, Ted. Questions from the floor? Right, there we are, straight away. Ted, come and stand in the middle somewhere, then you've got the microphone as well.
I've been one of the few that has been injured by a meteorite, but only because it was on the shelf and I was using one hand with a vacuum cleaner while attempting to move the other. It fell off the shelf, landed on my foot, and because I was just wondering, vacuum cleaning the shelf, is that all sort of meteoritic dust which is actually sort of falling down out of the through the atmosphere and then landing back on that shelf again? So I'll have to repeat the whole process again.
Yes, you would. Yeah, that's true. I mean, look, meteorites have injured people. I've recounted several examples in income of people who were sitting in their houses and suddenly something comes through the roof and bounces around the room and injures them. That has happened. But nobody has actually died as a result. It could be that, of course, somebody might have died as a result of dropping it on their foot and having to see it. I'm not sure about that. I don't think the statistics are collected. But and as for your shelf, yes, I'm afraid dust is unending.
Right, let's work our way around. There we go. Thank you.
Hello, I would draw issue with your definition of Occam's razor, and what you said is a commonly held belief about it, but if actually you research it, you did not say that the simplest explanation is more likely to be correct. What he said was, assuming the simplest explanation is the best way to proceed. He was actually defining a method, and that's the method of science. There's no a priori reason why nature should be simple. It might be, but you don't know that when you start.
Yeah, that's absolutely right. You're quite right to correct me. I was caricaturing the process in order to illustrate the way that geologists, particularly in this experiment, it's a guide to the way you should proceed, rather than a dogma. Yes, absolutely.
A lady here, Naomi. Can you reach? Pass the mic down.
Are meteorites responsible for early life? For example, amino peppered the Earth with amino acids, protein, and the other quick point is Tugunska in 1908 in Siberia. Would you accept that that was a meteorite?
Well, yes and yes. There's a chapter in the book about this. You hear me saying that a lot. There's a chapter in the book about this. But the idea that life on Earth was seeded from space is a very old and distinguished one. And as yet, there is no proof that it happened. But space is full of organic molecules, which is it's full of amino acids. This has come as a surprise to many people, and these things do survive their passage through the atmosphere. So, although the idea has existed for a long time, it has never been disproven. and it's difficult to know how it could be proven. It's one of those things that amino acids and all the necessary building blocks of life can arise spontaneously on Earth without the intervention of seeding from outer space. The thing is that panspermia, as it's known, is one of those theories that comes in various sort of hard and soft forms. The soft form is there are organic molecules which might have acted as the templates for organic molecules on Earth, and they were the building blocks, and life originated on Earth. That you might call the soft version of panspermia. The hard version of panspermia is basically bugs in space, viruses and things floating around, and they come. This is the sort of Fred Hoyle idea of how influenza outbreaks occur, and I think that there's very little scientific credence given to that side of panspermia. But to the other side of panspermia, it's one of those ideas that is still there. It's not difficult. It's not easy to prove it. It's not easy to disprove it. So it's just there as an idea, and the jury's still out. And as for Tunguska, yes, it was definitely a meteorite, but it was an air explosion meteorite, and the flattening of the trees. Nothing actually hit the ground. It was a rocky meteorite which exploded in midair, and the fireball that it created created the shock wave that flattened all those trees. So nothing actually touched the ground. It exploded in the atmosphere, which means that it was something of a few hundreds of meters across, which just blew up without trace.
Right, well, let's go just immediately to your right there, as you've got the... Oh, thanks.
You told that certain meteorites coming by 40 kilometers per second in velocity. My question is, after the collision, what will happen with the gravity? There will be on the place an anomalistic gravity, or a certain difference number?
Oh, that's a challenging question. Well, what happens when something that large, as I said, with all that kinetic energy, it immediately flashes, or all that kinetic energy turns to heat, which blasts the meteorite to pieces, so all its mass is then distributed into the atmosphere. So there's very little impact upon the surface of the Earth. It's mostly, all the material is blown into smithereens, and it's distributed around the atmosphere along with all the heat and the extra energy that goes into the atmosphere. So you will get you get an iridium anomaly, for example, and you will get spherules of molten rock, which will settle out and be found in deposits and so on. So it will be distributed widely around the Earth. So there won't be any effect upon local gravity or anything of that sort. I don't think, although you'd probably better talk to a physicist, and I don't claim to be one of those.
Thank you.
Thank you.
Right. Let's see if there's anybody at the back. Question at the back? Ah, there we are, back row.
If a very large meteor strikes the Earth, can we really say that it simply explodes into so much dust and does very little damage otherwise? Isn't it more likely that the mass will burst through the Earth's crust, cause substantial displacement of the magma beneath, and therefore set off quite separate earthquakes, volcanic action, which may last for millions of years just from that single meteor strike?
Well, that's an idea which has people have been thinking about it for a long time. The idea that you could have a crust penetrating meteorite that would actually go straight through the crust and cause, maybe even be the cause of a large igneous province eruption. Again, it's one of those ideas that it's quite beguiling. Nobody really knows whether it could possibly work. The impact physicists to whom I've talked don't tend to think that that's the way it works. There is enough. It would have to be such an improbably large meteorite asteroid to have those effects. That at this stage in the evolution of the solar system, that those such large bodies do not get deflected as a rule out of the asteroid belt. It would have to be, in other words, it would have to be something between 10 and 100 kilometers across, and that just doesn't happen. They're mostly up to 10 kilometers across, the ones which would really cause devastation on the Earth, and they would not have that effect. That they would not be. That their energy would be dissipated before they did very much damage to the crust and cause a kind of a piercing event, which would have plate tectonic repercussions. So it's probably a matter of scale. Again, because as I mentioned before, the higher the fewer, the larger the fewer when it comes to asteroids. They're just at this stage in the evolution of the solar system, there just aren't that many huge bodies drifting around. There were, certainly in the past, during the late heavy bombardment, there probably were space debris of that kind of dimension. But again, it's one of those things that you have to bear in mind that the solar system is also an evolving system. It isn't the same now as it always was. Even for things like there are not the radioactive isotopes that there used to be, because many of them have short half-lives and are now extinct. So you have differentiated asteroids of really quite small size, purely because aluminium-26, which was present in sufficient quantity at the origin of the solar system to heat them up and to allow them to differentiate into nickel-iron cores and rocky shells. That isotope is now extinct. It doesn't exist anywhere in nature anymore. So for that reason, you cannot get differentiated bodies of that size anymore. So conditions in the solar system have changed, and one of them, fortunately, is that there aren't that many. The larger objects are in stable orbits, and they don't tend to get deflected.
That's very reassuring, Ted.
I find it so.
Now,
it works for me.
The gentleman in the very front row here.
Thank you. Is it true that in the Nakla meteorite, the Egyptian one, killed a dog?
Oh, the Nakla dog. No. Yes. No. Well, the story about the Nakla dog, for those who don't know the story, a meteorite is supposed to have landed in Egypt and killed a dog. It was in a place called Nakla, and this deer creature is known as the Nakla dog. This dog, he's the favourite dog of all meteoriticists. People love the Nakla dog. Unfortunately, it appears that the reason this dog was brought into existence was the local wali of Nakla decided that the neighbouring village, where all the actual attention was being paid, that he needed some of the publicity too, and so invented the story about the Nakla dog in order to attract press attention to his village and just get a bit of backwash from the sort of global press interest in the meteorite fall. So it looks as though the Nakla dog, sadly, happily maybe, was not killed by the. Trees have been blown to bits. Animals have been injured. People have been injured, but nobody, not even a dog, has been killed. And it's a real shame because Nakla dog did. It is. I mean, the Nakla dog would have been the only, because the Nakla meteorite was actually a Martian meteorite. So it was a bit of Mars that had been splashed off Mars by another impact and which had found its way to Earth. So that would have made the Nakla dog the only Earthling ever to have been killed by a Martian. Which really neat, but sadly not true.
Ted, I think on that point we can draw our proceedings to a close. So perhaps you'd join me in thanking Dr. Nield.
I might just mention that if anybody wishes to purchase a copy, we're having a fire sale. On the way out, you can buy a copy for £10. Whoa. Half price, practically. And if they run out, I've got a few more.
Very good. Thanks.